Thank you, Nell. All right, so my talk is called Bootstrapping, and that's probably already raised a bunch of questions, like what is bootstrapping and what does it have to do with compilers? And so I'm going to talk about what it is first before we dive too deep into it. So the Rust compiler is written in Rust, which leads to some strange and interesting challenges. And because it's in Rust, that means you have to compile it with an existing Rust compiler. So you need to compile it with itself? Like how does this work? How do we compile the compiler with itself? Well, the way you do it is you can use an older version of the compiler. So some definitions real quick. The Rust compiler is self-hosted, which means it's written in Rust, the same language that it compiles. And bootstrapping is the process of building it. Okay. Right, so there's 3 parts of this talk. And the first part is how we want things to work, how they should work, how we hope they work. Right, so when I say an older version, the Rust compiler always uses the immediate previous version. So for example, Nightly is built with beta, beta is built by stable, and stable is built by the previous stable. And it goes back in a chain 1 at a time. And you might ask, why are we going 1 at a time? Like, wouldn't it be simpler if we just had one version of the Rust compiler that we always used, pinned that in place, and there we go, we never need to update it? Well, the problem with that is that we use unstable features in the compiler. But let's go ahead, let's try it out and see what happens. We're going to build the current beta compiler, 1.63, with the previous stable compiler. This is like only 2 versions back, like how bad could it be, right? It can't be that bad. Well, oops. so if we look at the error here, it's telling us there's something called a language item that we need to know, and it's called from yeet, and we don't know what from yeet is, and this is like something in 1.62, not in 1.61. So like even in that short amount of time, we're already running into errors. And because we depend on those unstable features in the compiler, we can't use that older version. But like, what does this mean, right? Like, what are language items, like all this stuff? So some more definitions. Standard is the standard library. If you look at this error here, it's not actually pointing to the compiler. It's pointing to the standard library. And what's going on here is the standard library depends on implementation details of the compiler, and one of those is language items. So let's take an example here. This is the addition trait. It's defined in core. It's how you do operator overloading in Rust. And for the most part, it's a normal trait. You have an output type that tells you the type of the result. It has a function you implement that tells the compiler how to calculate the result. And you can do it for any of your user-defined types, just like any other trait. But what makes it special is the little attribute at the top, language equals add. And what that does is it's a little bit of compiler internal magic that says this trait corresponds to the addition operator. And we need this to make operator overloading work, so you can use a plus instead of a function. But it also means that we're depending on implementation details of the compiler that can change in any release. We don't stabilize stuff like this, because you're not meant to use it unstable. We want to be able to make breaking changes in case we find a better way or faster way or whatever to implement this. And there's lots of things like this. It's not just operator overloading. The library depends on Rust stock internals, so we can document primitives and keywords. We have intrinsics. If you look at the error earlier, we have some intrinsic functions that were added in 1.62. And all sorts of other things. And because the standard library is so tied in with the compiler itself, you can almost think of it as part of the compiler. If we define this addition trait in any other way, if we remove the output type, or if we change the function signature, we won't be able to compile it. We won't be able to implement operator overloading. It's important that it looks exactly the way that it does. And now you might ask, like, what happens if we do change these implementation details, right? We said earlier the reason they're unstable is because we might want to change them. And so if we do change them, won't it break the standard library, right? Because it's depending on unstable features. And the reason this is okay is because we only ever build the standard library with one version of the compiler. It only has to support 1.62, not any later version. And so it knows how the compiler is implemented, and it can write code in exactly the way that it knows the compiler will accept. Right, so let's take another look at the error. We've talked about language items, we've talked about intrinsic functions, we've seen this is in the standard library. And I want to point out something strange here. We're building the standard library before we build the compiler. Now, this is different from any other program that you would write in Rust. In a normal program, you have a hello world, and you use functions from the standard library just like you would anywhere else. And the standard library is kind of automatically present for you when we ship it to you through RustUp or through your distro or wherever. Why is the compiler different? And the reason is, when we build the compiler, we are not using the beta compiler, we are using the nightly standard library. And the reason we do that is because it lets us dog food new nightly features, even as they're added, without waiting for beta release. And so the way this works is we have the beta compiler, which builds the standard library, and then the new standard library is used with the beta compiler to build standard. And again, this is unlike any other program in that we're building the standard library before we build the nightly compiler. Right, so I've talked so far about how the standard library depends on implementation details, about how we dog food those unstable features so we can use them in the compiler. And there's another way we dog food features, and that's by using language features in the compiler. We do this on nightly even before the beta release. As soon as someone adds a new feature to the compiler, we can immediately start using it. How is that possible, right? How do you use these language features when you're compiling with the beta compiler? And the answer is you don't use the beta compiler. We use something called staging, which is we use two different compilers to build RustC. So the way this works is first we build the standard library with the beta compiler, like I talked about earlier. Then we use the beta compiler and the newly compiled nightly standard library to build the nightly compiler, so we can start using library features. Then we rebuild the standard library with the nightly compiler. And now, if you look at this, you might think that's kind of weird. Why are we rebuilding the standard library when we've already built it? There's a great reason for that. And the reason is magic ABI reasons. I'm not going to go into ABIs and why this is important in this talk, but I'm happy to answer on Discord or after the talk. Right, so then we rebuild the standard library. We use that newly compiled standard library to build the compiler again using the nightly compiler. And what that lets us do is use language features in the nightly compiler. So let's take a concrete example. Say we stabilize a feature. This is derive default enum, which lets you derive default on an enum. It was stabilized in 1.62. And so when we're building 1.62, well, the numbers here are wrong, but when we're building the nightly compiler with the beta compiler, we need to enable the feature when we use it, because the beta compiler still thinks it's unstable. It hasn't been stabilized on beta, it's only been stabilized on nightly. But when we rebuild the nightly compiler with itself, the nightly compiler does think that it's stable. And so we can disable the feature, so we don't get a warning about an unused nightly feature. And that's what this attribute does. It says enable the feature exactly when we're using the beta compiler and not nightly. All right, I've talked so far about how this works in theory, how we want it to work, how it should work. Now we're going to talk about what happens when it doesn't work. What happens when someone introduces a bug to the compiler? Most of the time, it'll be caught by our test suite. We have a lot of tests. They run in every merge. They run in every platform. We catch a lot of bugs this way. But not everything's covered by tests. Sometimes things slip through. Usually things just break your program. It fails to compile, you get an error, you report the error, we fix it. But sometimes you get a worse kind of error, and that's when the program still compiles, but it does the wrong thing at runtime. And that's called miscompilation. So let's step through how that happens when we miscompile the compiler itself. First, the PR gets merged. We build a compiler source with the bug. So now any code that it compiles will have this bug. Then it builds the standard library, rebuilds itself with that standard library. And note here that the standard library now could have bugs introduced into it that aren't present in the source because the compiler is buggy. It did something wrong, and now the standard library no longer matches your source code. And even more than that, the compiler was rebuilt with itself with a version of it that was buggy. And so now it can have new bugs that are even unrelated to the original bugs. Like there's no limit on how buggy it can be, right? Other than the test suite. So that's not great. But in practice, this rarely happens. We have a lot of tests. We have a lot of great reviewers who catch bugs in PRs. And we have something called a release train, nightly and beta and stable. And that gives people a lot of time to report bugs and let us fix them before they impact users on stable. There's a great talk by Pietro Albini in 2019 called Shipping a Compiler Every 6 Weeks. Highly recommend looking that up if you're interested in how the release process works. Now, there's another type of bug, which is when we miss a bug, it makes it past tests, it gets merged to nightly. But when we try and build the next version of the compiler, when we promote nightly to beta, we can't compile the new nightly compiler. So we merge the PR, we publish the beta release, we start building nightly with beta, and at this point we hit an error, and we're like, why are we hitting an error, right? Like we know this just worked before. And at this point we'll discover the miscompilation, we'll be like, okay, we did something wrong, we fixed the bug, and then we'll patch the beta compiler, which is called backporting, and then we'll use that new patched compiler, and then we can get it to work. Okay, so I've talked about bugs that occur pretty frequently in practice, bugs that cause compile errors, bugs that cause miscompilations, and we know what those look like. We know how to fix them, we have experience dealing with them. Now I want to talk about a kind of bug that's still theoretically possible, but a lot harder to detect or to fix. And to do that, I need to take a detour and talk about some compiler theory, but I promise it does have practical implications. Just stay with me for a bit. You may recognize this guy. His name is Ken Thompson. He's done a lot of stuff. He's written the Unix operating system. He helped work on the C programming language in the 70s. And he also wrote a little pamphlet called Reflections on Trusting Trust. Now, while Ken Thompson was working on C, he's of course involved with the C compiler. And while he's working on it, he gets this kind of intuition about language features work. He's like, when you add a new feature, it's like you're teaching the compiler about the language. So let's take a concrete example. Let's say that we add a new line character to the Rust language. I have some pseudocode here of basically what that would look like. You have a function, it takes its input, which is a string. You parse the string, you see like a \n, you're like, okay, this is a new line character. And so the very first time you add support for this feature, the new line character is not in the Rust language because you haven't added that support yet. And so you can't write it in the output code. You have to write the actual value instead, which is OX0A in ASCII. But the next time, when you recompile the compiler, because it's written in Rust, now it has the feature, and you no longer need to write the value in the source code. You can just write \n like any other program would. And that's great. That means that you can add lots of features to the language, and you can add syntax sugar and make it easier to use and that sort of thing. But it also means that your program source is like not exactly what's in the final binary, right? You have the character literal, which is a symbolic representation of the value, but not the value itself. What happens when instead of a feature, it's a malicious compiler? And so what goes on here is you can have a compiler that takes your source that you reviewed and you know is correct and does what you want to, and you take a compiler that does not generate a program that corresponds to that source. Then you end up with a program that looks like it should be trustworthy, but is not in fact trustworthy. And so there's a solution here, and the solution is you just read the source of the compiler. You're like, okay, well, I've looked at it, I've read through rustc or whatever, it's good, I'm glad, great, problem solved. Well, not quite. What happens if the program you're generating is itself a compiler? What goes wrong here is you take your trusted compiler, rustc, you compile it with an older version with some malicious compiler, and you end up with a backdoored compiler that looks like it's trustworthy, but doesn't do what it says. Then you take your trusted program, which you've reviewed and you're pretty sure is correct, and you compile that with the backdoored compiler, and you end up with a binary that looks like it should be trustworthy, because reviewed it and the compiler that creates it, but still is not trustworthy. Like, how do you avoid this sort of issue? The answer to that is you keep going up the chain. You keep reading more and more compiler sources. You're like, okay, I've reviewed them. Every single compiler ever used in the history of my program looks good. We're pretty sure it's trustworthy. This is called a trust chain. All those compilers in the history of your program are a trust chain. The problem for Rust is our trust chain is pretty long. And not only is it pretty long, but it kind of trails off. In 2012, we kind of forget releases come before that. You'd have to like go through the build system and like read the source of the make files by hand. Like it would be like a very involved process to try and go back that far. So that's great. But there's a solution to this. There's a guy named David A. Wheeler. In 2009, he came up with an idea called diverse double compilation. And the basic idea is you take a bunch of compilers and you compile them with each other. You're like, if we compile Clang with GCC, compile that with GCC again, compile Clang again, if we end up with the same compiler as we had originally, then we're pretty sure it's trustworthy. It's like very, very hard to sneak a bug through that way. The problem for Rust is we don't have multiple compilers. We only have one compiler, the official compiler. That's fine. Everything's fine. It's probably not a big deal. I seem to have messed up my slides. There we go. All right. Everything's fine. Well, it's not quite true that we only have one compiler. There's something called mrustc, which is a C++ compiler, which compiles Rust. It's written in C++, compiles Rust, and so from there, we can use existing trust chains. C++ is a lot easier to establish trust chains for, because you only have to go back 4 or 5 compilers instead of 100 or so. And people use this in practice. Google and Amazon and Facebook and all the big companies have their own trust chains that already exist. And they can start at mrustc, go forward, and establish a trust chain for the Rust compiler. And because C++ has multiple compilers, they can also do a shorter thing, which is just verify them against each other. They don't need the trust chain unless they want to. Right, but there's a problem still, which is that mrustc is kind of a one-person project right now, and so it can't keep up with all the nightly features that the Rust compiler is adding on every 6 weeks. Now, it does support pretty recent versions. It supports 1.54, but in practice, that's still like 10 or so versions of the compiler. Now, I don't know how many of you have tried to compile rustc from source, but it takes a while. If you compile it 10 times, that's probably a full day of running your computer nonstop right there. But it does work. You can do it if you want to. Now I'm going to talk about future ideas for the language and for bootstrapping the compiler. So not only do we have mrustc, in the last month or so, there's actually the GCCRS front end, which was merged into GCC master. Now GCCRS right now is still pretty experimental. It passes about half of the tests in the rustc test suite. But in 2 or 3 years, I think it's very possible that it could be another source for the trust chain, and it would let us compile and establish that trust chain with a lot fewer steps. You wouldn't have to compile rustc 10 different times, which is great. And it also lets us verify the compilers against each other and make sure they don't have bugs, that sort of thing. Okay, I'm going to switch tacks for a bit. I'm going to switch away from trusting trust. I talked a bit earlier about how we use beta to compile nightly, but I didn't mention where beta comes from, right? Like most people who are working on the compiler itself don't have beta installed, right? They use nightly, sometimes they use stable. We actually have a lot of trouble getting people to use beta because most of them use stable in production. Or if they do want features, they're using nightly. It's hard to get people to use beta. So how do we get it onto people's systems so we can use it? And the answer is we just download it. We have a little Python script that reaches out to a website. It downloads the beta compiler. It builds our build system. Then the build system uses the beta compiler to build the standard library. And that works great. We've done this for ages. The problem is that now we have a Python script, right? If you're working on the compiler, you probably don't want to have Python installed. It's not part of your normal workflow. You have to figure out like Python 1 versus 2 versus 3, and you're like, wait, what if Python doesn't have a version number? And like it turns out that there is no version of Python with a name that exists on every platform. It's like a whole mess. And I got really frustrated at this. In like January of this year, I'm like, okay, I'm fixing this. I'm getting rid of this problem. And so instead of using Python, I had the idea, what if we just use the compiler people already have installed? Most people working on Rust use Rust regularly, which is why they contribute to the language. So we can just use the Rust they already have installed. Take that, build the beta compiler, build our build system, and there we go. And I've been working on that for about 6 months now, and it's going pretty well. This is the tracking issue. As you can see, it has 6 of 11 tasks checked. This is making good progress here. If anyone is interested in working on this, by the way, please do reach out to me. I would love to help people get involved in the project and help out with this problem. All right, that's it for me. A little about me. My name is Joshua Nelson. I work at a company called Cloudflare that does computer networking. And I've been involved with the project for 3 or 4 years now. I started with docs.rs, the documentation site. I worked on RustDoc, the documentation generator. And most recently, I work on bootstrapping. Thank you all.